Section 7-5 is on numerical solutions of differential equations using Euler's method. And the objective of this section is, given a differential equation and its slope field, approximate points on a particular solution. If you recall, in the last section we were solving differential equations using a graphical method. And we were given an initial condition. We started at that point, and based on the slope field that we were given, we used it to help us sketch a curve that goes through that slope field. The difficulty that we encountered is the fact that we are all coming up with slightly different sketches. They were similar, but they were slightly different. The advantage of moving to a numerical solution is now we're going to have a more formula-based or formula-driven method, so that we all come up with the same points that this solution has to go through, and thus our curves always look the same for us between from one student to the next. All right, so let's talk about this method here. The method here is called Euler's method, and it's based on this idea of local linearity. We've used that term before. That's the term we use to describe a function that's differentiable at a particular point. Local linearity means that as you zoom in on a particular point, that's the local part, that the function starts to look more and more like a straight line. That's the linearity part, local linearity. And it turns out that if your function has local linearity, it's differentiable as well. And I can use this idea in the fact that if I know one point, that the linear function, the tangent line from that point, is a pretty good point line that I can follow to get to the next point. It's going to be a slight error, but that linearization of that function at that point is a pretty good approximation. And we can repeat that process several times to get me to the next point and the next point and the next point. Use the slope at one point to figure out where I should end up for the next point. And I can illustrate that here with an example. So you start out with some differential equation. We'll say dy dx is equal to some function of x and y. And you're also given some initial condition. We'll call that x sub 0, y sub 0. And given those two pieces of information, I can come up with a sketch of a particular solution. So let's say that x sub 0, y sub 0 is maybe up here. Oops, x sub 0 and y sub 0. Okay. And what I can do is I can use that differential equation and plug in my initial condition and find the slope. The slope at this point, maybe it's pointing maybe out in this direction here. All right. Given some change in x, this distance between these 2 points here, this is a point here for us. That distance, that horizontal distance there, is our change in x, our dx. And from that slope and the change in x, we can calculate the corresponding change in y. We call this our dy. The distance right here is dy. In order to figure out where that next point is at. And this next point we call x sub 1, y sub 1. And then I can repeat this process. I can again use my differential equation to come up with the slope to the next point, which is probably not going to be exactly the same. So let's say there's a slight difference there. That's a little bit, there's not much of a difference between those two, but is a slight difference there. And again, this is that distance dx is what I'm using here. These are supposed to be the same distances here is what I want it to do. And again, I can calculate the corresponding change in y here. This is our dy, to help us find out where the location of this next point is, which we'll call x2, y2. And once I come up with this series of points, I can then sketch a curve that goes through those points and thus have a pretty good sketch of the solution. That's the idea of Euler's method. So let's go through the steps of what Euler says to do. The first step that he says is to solve your differential equation for dy in terms of x, y, and dx. That's usually the easy step, because you usually are going to start out with an equation that's already got dy over dx on one side. So literally all you have to do is move the dx to the other side. Okay, if I go back up here to my example, literally all I have to do is take this guy right here and multiply both sides by him to move him to the other side. Now if it's not solved for dy dx, then obviously you got a little algebra to do first before you can do that step. All right, once you have that, you can then substitute in the values for x, y, and dx to calculate the corresponding value of dy. Again, if I know where I'm starting at x and y, and I know how far horizontally, that's dx that I want to move, if I can calculate dy, that tells me how much vertically I need to move, and thus I can figure out where the next point is at. And the way to calculate where the next point is at is you find the next x value by adding your dx to the previous x. So if I take my old x value and add dx to it, it gives me my new x value. And this is the easy one to calculate because of the fact that generally speaking, before the problem even starts, you know what x is for the initial condition, and you know dx for every single one that you're going to calculate, so you can immediately start rattling off what the new x values are going to be. The y values got a little bit more to do because we have to first calculate dy, which we did in step 2. But once I have that value, I can find the next y value by adding dy to the previous y. In other words, you find the new y value by taking the old y value and adding dy to it. And now we've got a new point, a new x and a new y. And now we can take those points and we can plot them. And we can continue this process. This is a repetitive process. So the last step of this is to keep repeating this. Repeat steps 2 through 4 to find the next xy point. And once you get that point, you plug that back in and repeat the process. And it keeps going on over and over again. Whatever your new output is, your new x and y value, those become the input the next time around. All right, so let's try an example here. If you look in the example here, example 1, says the figure there shows the slope field for the differential equation dy dx equals 0.5 times x plus y. All right, so let's write down our differential equation here. Let me just put this down below this graph here. So we have dy dx is equal to 0.5 times x plus y. And for part A, it says use Euler's method with dx equal to 0.2 to calculate the approximate values for y for the particular solution containing the point 0, 0.4. There's your initial condition. And they want us to go from 0.2 all the way to 1.2. All right, so the first step of this, remember, is to first solve this equation for dy. So I'm going to go ahead and do that first. So we have dy is equal to, again, the first step is to just simply move the dx to the other side. So I just have to literally multiply both sides by that to move it over there. So it's going to be 0.5 times x plus y times dx. We only have to do that once. We've done it. We're done. All right, so for part A, let's write down the values they've given us. They gave us a dx value of 0.2. Most problems we're going to see they'll give you that. If they don't, then you have to pick a small number for a change in x. The smaller you make it, the better your approximation. However, the more points you might have to calculate to get a full graph that you want. So they gave us that dx is 0.2, and then they gave us the initial condition, that is that at x is 0, y is equal to 0.4. And I'm going to write it out a different way here for us, and if it helps you to do it this way, you do it that way as well. But I'm going to call this x sub 0 is 0, and then y sub 0 is 0.4. So they'll give us names for each of these points as we come up with them. All right, so the process that we want to go through is finding the next point. I know where I'm starting. In fact, I'm going to go back to my graph here and actually sketch or mark that point. At x equals 0, y is 0.4. So x equals 0, y equals 0.4. There's that point that they're talking about. And literally what I want to do is I want to come up with several points here that I can plot and then sketch a curve that goes through those points. This is a repetitive process that we've got to go through here, though, so I'm going to just call this step 1 here of this process to find actually the next point. So the first thing we need to do is to find out what dy equals. So to find out what dy equals, you take your x, your y, and your dx, and you plug it into your equation here for what dy is equal to. Plug it into this guy right here. So dy is equal to 0.5 times x plus y. Well, x, actually I'm going to write it out this way first. We'll call it x sub 0 plus y sub 0 times your dx. Go ahead and write the formula, and then we'll plug in the values. All right, so for our problem, x sub 0 was 0, y sub 0 was 0.4, and dx was 0.2. So just plug in the values that you were given, and now calculate your corresponding value for dy. So if we take 0.4 times 0.5 times 0.2, let me just go ahead and punch that in the calculator. 0.5 times 0.4 times 0.2, we get 0.04. So there's our change in y. Now that's part of what we want to do. Really what we want to do is find out what the next value for x and y are. So I'm going to use that to calculate x1 and y1. So x1, remember, is the old x value. That would be x sub 0 plus my change in x, my dx. So my previous x value was 0. My change in x value, my dx that is 0.2. So we get a value of 0.2. This is the easy one, by the way. In fact, when you start the problem, you know all these x values. Since I'm starting at x equals 0 and I'm changing x by 0.2, that's dx, I know that my x value is going to be 0, 0.2, 0.4, 0.6, 0.8, and so forth. I can easily calculate those. The ones that I've got to work at here are the y values, because I have to first do this calculation to find out what dy equals, because to find out the next y value, that is y1, it's equal to y sub 0, my initial y value, plus that change in y we just calculated. So my y sub 0 was 0.4. The change in y we just came up with was 0.04. And so we end up with 0.44 is our value there. So now I have another point to plot. That right there is an xy value. So let's go back up to our graph and plot at x equals 0.2, y is 0.44. So at x equals 0.2, y is 0.44. That's going to be about a quarter of the way up there between 0.4 and 0.6. So we'll say it's about right there. Got 2 points down. We got to get several more. How do we get several more? Well, we repeat this process. So the second iteration of this. First thing you got to do is calculate dy. dy is equal to 0.5 times now x sub 1 plus y sub 1. We take the last value that we just calculated and use it as the new input. So this turns out to be 0.5 times x sub 1 is 0.2 plus y sub 1 is 0.44 times my dx, that's 0.2. And again, I'm going to punch that into my calculator just to get that value. So we have 0.5 times 0.2 plus 0.44 times the 0.2. And we get 0.064. Oops. All right. 0.064. So now, let's calculate the next x and y value. Based on the work that I just did there, I should be able to do that. X sub 2 is equal to x sub 1 plus my change in x. Again, this is the easy part. X sub 1 was 0.2. My change in x was 0.2. That is the dx, so we get 0.4. Again, that's the one that we said was the easy one to calculate. Y2 is going to be y1 plus dx. Oops, excuse me, it's not dx, it's dy. Change in y. And so y1 was the 0.44. The change in y, the dy we just calculated, was 0.064. So if we add those together, we get what? 0.504. There's another point for us to plot. At x equals 0.4, y is 0.504. So at 0.4, we're going to be about halfway, just above halfway between 0.4 and 0.6. And you can see the process that we're going through. Okay, use one point to help me calculate the next point. All right, this process you can see is going to take a while to go through and find all these points. So to help us out, as we've done in the past, I'm going to give you a program that will help us speed up this process. So let's go to our calculator and try running that program. So in order to run the program, the first thing you have to do is in y1, we have to put our equation. So our equation that they gave us here was 0.5 times x plus y. And the equation that you type in here has to be in terms of x and y. So if they give you an equation for time and population, you got to convert your t's over to x's and your p's over to y values, or whatever the problem is. You got to be able to convert to x's and y's. All right, so let's run our program here. It's a program called Euler. And Euler asks us, first of all, it says that y1's got to be a function of x and y, which is what we've got. And it asks us for our initial conditions here. So x was equal to 0 initially, and y was equal to 0.4. And that's going to ask you for your change in x, which is 0.2. And then finally, it asks you for what's the last x value you want to calculate, so I'll put 1.2. All right, and that's going to go through several screens showing us the corresponding x and y values. So it shows you initially that x is 0, y is 0.4. That's because that's the initial values we gave it. dx we also gave it. That's going to stay the same on each screen here as we go through this. In fact, that's the only thing that's going to stay the same. dy, it calculates, was 0.04, and it's going to use that to help us come up with the next point. Notice, by the way, that that 0.04 is the calculation we first did. If I go back to our first calculation right here, there's our change in y was 0.04. That's the same thing our calculator's given us there. And when I press enter, notice that the next point that it gives us, x is 0.2 and y is 0.44. There's the calculation over on the right that we came up with for that second point. And notice that it gives us the calculation then for dx we know, but dy is 0.064. And so if you look at your second calculation here, we had that dy was 0.064. And finally, if we press enter, it gives us the next point there was at 0.4 for x and 0.504 for y. So those are the same. All right, I'm just going to go through and get these values and then plot them on our graph up above. So it's at 0.6, it's at 0.5944. So it's just slightly below 0.6, so we'll say that's about right here. Let's go back to the calculator, we'll press enter. And at 0.8, we're at 0.71. 0.8, 0.71, that's slightly more than halfway, not much above halfway, between 0.6 and 0.8. Let's press enter again. So at 1, we get a value of 0.865. So 0.865, that's again about a quarter of the way between 0.8 and 1. And finally, the last value that we get, at 1.2, we get 1.05. So just slightly more than 1. It's going to be about right here. Okay, and then what we can do is we can actually sketch the curve that goes through these. All right, which is really what part B is asking us to do, draw this approximate particular solution on a copy of the graph there. So now if I sketch the curve that goes through those points, it's going to look something about like this. There would be our solution, our particular solution to this differential equation, given this initial condition. Of course, as we change that initial condition, we're going to get a slightly different sketch. All right, let me go back to the calculator here real quick and just show you what it gives you at the very end. And when you've done running your program, you'll see that it gives you x is contained in list 1, your y values are in list 2, and your change in y, your dy's, are in list 3. If you want those, you can access those. And the nice thing about those actually is if you go to your stat plot, since it dumped these values into list 1 and list 2, I can turn on stat plot 1 and using my, in fact, I'll use the connected scatter plot here using list 1 and list 2, and let me change this to a bigger mark here just so it's a little easier to see. We can go to our window, and we were working from 0 to 1.2, so let me go from negative 0.1 to 1.3, just so we can see a little bit on each side of this. And we'll do the same thing for our y values. Oops, that should be 1.3. And now if I graph this, it will show me that particular solution there. And notice that's the same particular solution that we got right here. All right. The last part of the question here that they ask us on example 1 is, does the approximate solution overestimate or underestimate the actual solution? And you can tell that by looking at the concavity of your solution. I guess I should stay at the graph there. You can see that our graph is concave up. And based on that, I can use it to help me understand whether this is going to be overestimating or underestimating. Again, it's still an approximation. But because my graph is concave up, which looks like this, if I pick some point on my graph and use the tangent line right there, which is, again, what we're basically doing here. We're using the tangent line to figure out the slope at one point to project what's happening at a different point. I'm using my tangent line at this first point to figure out what's happening later on at this other point. And you can see that I'm off a little bit. The actual solution, let me do this in green, is up here. So you can see that in this case, because of the fact that we are concave up, this is an underestimate. It underestimates it. If I was concave down, which looks something like this, and I again pick some point, let's say we start right here, and use the tangent line to approximate what's happening later on. Say we'll go out to this point right here. You can see now I'm above the curve. I should actually be down here, but my tangent line's above the curve at that point, so this overestimates. Okay. And that's the end of that example. Let me just show you real quick 2 other things I'm going to give you here as far as programs are concerned. You'll get a program called Slope Field. And Slope Field does exactly what its name describes there. It will sketch a slope field for you. So if I run that program, it's going to tell you that y1 has to contain a function of x and y, and that the scale is important here. Whatever you set as your scale will determine the density here of your slope field. If it's too large, you're not going to get much. If it's too small, you're going to get way too much. Okay, so there's kind of a fine line that you have to tread there to figure this out. But I would say if you have a slope field that has got, like this one has about 25 different points, it looks like, or actually it's closer to 30, right? 36 points that it's plotting. That's not bad. Okay, so there's the slope field. You'll also get one called Euler field, which is taking a slope field and drawing your solution from Euler's method in there. So again, it tells you the same thing at the beginning, but it's going to ask you for these initial conditions again. So x was 0, y was 0.4, and dx was 0.2. But it also asks you how far to the left and to the right do you want to sketch this. I want to go from 0 on the left to 1.2 on the right. And then it will sketch your solution along with the slope field. And those 2 little programs there will be very nice for doing some problems in this section. All right, that's the end of this section.